Welcome to the fourth of four lectures on power system planning. I'm Hyde Merrill. This lecture is on robustness versus cascading blackouts. When the sun came up on Wednesday, the 14th of August, 2003, it was clear that it was going to be a typical August day in Ohio. Hot, sticky, demand for power would be high, a lot of power would be moving across the system. Things started going bad for the power system shortly after 12 noon. In the Midwest Interconnected System Operator Control Center, the state estimator stopped converging. The dispatchers were concerned. They called their programmer. He took the program out of service, checked it out for an hour, came to the conclusion that the state estimator was working correctly, and so advised the dispatchers. The problem was, he said, that the dispatchers had neglected to tell the state estimator that an important transmission line had failed and been taken out of service. He then left hurriedly for a late lunch, unfortunately forgetting to turn the state estimator back on again before he left. The control center operated half blind for the rest of the afternoon. Shortly after noon, also, the voltages were depressed in the Cleveland area. The operator of the East Lake 5 generating unit attempted to correct this by increasing the reactive power of his unit. Unfortunately, he asked his generator for more than it was capable of providing, and so to protect the generator, automatic equipment took it out of service. And it was out of service for the rest of the afternoon. Starting at about 2:15, various pieces of the computer system in the control center of First Energy Corporation, a utility in northern Ohio, began failing. The failures included both the primary and backup servers that processed alarms. For more than an hour, no one in the First Energy control room realized that their system wasn't working properly, that the computers weren't working, and they were blissfully unaware that the largest blackout in history was about to occur. Their system was collapsing around their ears, and the First Energy would get most of the blame for it. Between 3 o'clock and 4 o'clock, three important First Energy transmission lines, 345 kV lines in northern Ohio, went out of service. During the same period, all of the 138 kV system in northern Ohio collapsed electrically. The power system reached the point of no return at 5 minutes after 4. Within 10 minutes, the system had broken up into islands, and each of the islands went black, and 50 million people in Ohio and several surrounding states and the province of Canada were out of service. In the United States, it took 4 days to restore electric service to all the customers. In Ontario, they were still having rotating blackouts a week later. The total economic cost of the blackout in the United States was estimated at between $4 billion and $10 billion. In Canada, it had a measurable effect on the gross national product. In this lecture, we're going to talk about what causes cascading blackouts. We'll see that they are a phenomena of an energy conversion system of 3 elements. And P.S., it's a large system problem. Big is different. We'll show how modern network theory can do something that traditional models don't do conveniently. That modern network theory can model robustness, or the vulnerability of the system to cascading, and can lead to reducing the vulnerability to cascading. I'm going to begin by telling you about several blackouts. This isn't just for entertainment. Please pay special attention, because I'm going to ask you afterward, what are the real causes of blackouts? The granddaddy of them all was in northeast North America on the 9th of November of 1965. 5 transmission lines were carrying power from plants in the Niagara Falls area to Toronto. On one of these lines, a relay was set too low. And although the line wasn't overloaded, the relay detected that it was, and it took the line out of service to protect the line from damage. The power that line was carrying was instantaneously redistributed over the remaining 4 lines. One of those lines overloaded and was also taken out of service automatically. Its power was redistributed over the other 3 lines, and one by one, within 2.5 seconds, all 5 of the lines went out of service. Power to 30 million people was interrupted. It took 13 hours to restore service to everybody. Early Sunday morning, on the 28th of September 2003, Italy was importing a large block of power from France. It was actually importing 300 megawatts more than it had contracted to import. And as a result, lines got warm and expanded and sagged. And at 1 minute after 3 o'clock in the morning, one of the lines sagged so far that it came in contact with a tree. The short circuit caused the line to be taken out of service. About 10 minutes later, the Swiss operators, these transmission lines went through Switzerland. About 10 minutes later, the Swiss operators called the Italians and asked them to reduce their imports from France. The Italian operators didn't respond adequately. They reduced their imports to the contractual level, but the contractual level assumed that all of the lines would be in service, and one of them had shorted out. As a result, the other lines were still overloaded, and at 25 minutes after 3, a second line sagged into a tree. Within 12 seconds, Italy was isolated from the rest of Europe. Most of Italy, everything except for the island of Sardinia, went black within 2.5 minutes. Blackouts that didn't occur are as interesting as the ones that did. One of the famous ones that didn't occur was on Palm Sunday in April of 1965, about 6 months before the famous Northeast blackout. 37 tornadoes ripped through the service territory of the American Electric Power Company in Ohio. Hundreds of people were killed, thousands were injured. 77 towers, transmission towers, were wrecked. 2 substations were destroyed. 27 high voltage lines went out of service, and there was no cascading failure. There's never been a cascading failure in Texas. Incidentally, Texas is a small, isolated system. It's not connected synchronously with the United States. Before I ask you to tell me why blackouts occurred and why they didn't occur, let me define or describe the power system for you. The power system is a man-machine energy conversion system made of 3 elements. First, there's hardware that generates and carries electric current. Secondly, control and protective devices. And third, practices and procedures. Now, having defined the system, what are the real causes of blackouts? That's correct. Blackouts are always initiated by failures in elements number 2 and 3. At a time when the system is stressed, generally with heavy interregional transfers. Well, why didn't the Palm Sunday blackouts occur? Why was no blackout on Palm Sunday with all those tornadoes? Well, the system wasn't stressed. It was Sunday. It was in April. There was no air conditioning. There was no electric heating. Not much power was moving around the system, and so the system was able to withstand the loss of 27 lines. What about Texas? Well, Texas is a small system, and it turns out that small is different. Back in 1970, Vannevar Bush, arguably the brightest, most brilliant electrical engineer of the 20th century, observed that the more complex a society, the more chance there is that it'll get fouled up. And specifically, power systems have grown enormously and have become interconnected over vast regions. And we have had 2 severe blackouts and are undoubtedly headed for more. So this is our diagnosis. And next, our prescription. We'll leave to 1,000 engineers and managers the improvements in control and protective devices and the ordering of practices and procedures. Without expecting or even hoping for perfection, in either arena. We will turn to the mystery of stress, to the baleful effect of size, to guide us in designing and piloting a power system that is innately more robust, that is innately immune to the unavoidable imperfections in its constituent elements. We'll do this using modern network theory. Traditional methods have been used by thousands of power engineers and many utilities to try and reduce the number of blackouts. And they've been successful. And yet, the blackouts are still occurring. And we'll show how network theory can provide information that traditional methods can't provide, and can guide us in ways that traditional methods can't guide us. Modern network theory responds to three observations. First, there are a lot of large networks around. Second, by definition, they're too large to draw and study elementally, piece by piece. And third, biggest difference, the large networks behave in ways that are qualitatively different from the ways small networks behave. And from these three conclusions, there are three observations and conclusion. And the conclusion is that to understand large networks, you study their statistical and structural properties. And by statistical, I don't mean probabilistic. Here are some examples of three large networks. The first one is a food chain in a pond. Who eats and who gets eaten. Second, communication in a lab. These networks are made up of vertices and edges. A vertex is a place where things happen, and an edge is shows how things happen at one vertex influence another vertex. Obviously, the power system can be modeled this way, and it has been for generations. And the traditional models have vertices, which are buses, for instance, substations, and the edges are transmission lines or transformers. And models of this kind are based on a matrix called the bus admittance matrix. The bus admittance matrix has some interesting properties. First, for a large system, it's very sparse. Each row and each column of the bus admittance matrix is associated with a bus. And the non-zero elements of the bus admittance matrix are associated with buses that are directly connected to each other through a line or a transformer. Now, why is it sparse? It's sparse because in a large system, say 20,000 buses, each bus is connected to maybe, I don't know, 3 or 4 or 5 other buses on the average. And so each row and each column associated with a particular bus has 20,000 zero elements and 4 or 5 or 6 non-zero elements. Y-bus is symmetrical. And what Y-bus does is it computes how changes in the injections of the buses, changes in demand or generation, affect the voltages of the buses. And once we know how voltages are affected by changes in generation or demand, we can calculate using Ohm's law how the power flows on the lines and transformers change. This is tremendously useful. There are all sorts of analytical models based on Y-bus that are used every day in system planning and system operation. Unfortunately, they're so powerful and they're used so frequently that we tend to forget that that Y-bus isn't the only way of representing or modeling the power system. In particular, it's not a particularly friendly way to look at cascading failures. See, in a cascading failure, we're not really concerned with what happens when the output of a generator changes or when the demand changes. We're not concerned about how that affects the flows on the transmission system. What we really care about is what happens when the system itself changes. What happens when a line goes out of service? How does that affect the flows on the other lines? And Y-bus models don't measure this very conveniently. There's another model that does. It defines a different way of looking at the network. It's based on something called line outage distribution factors. DFACs measure the changes in flows on transmission lines that stay in service when some line has an outage and goes out of service. To use the DFACs, we measure or compute all of the flows with all the lines in service. We call this F naught. And then the post-outage flows for the outage of line J on some other line, line I, are the pre-outage flows on line I plus the DFACs between line J and line I multiplied by the pre-outage flows on line J. These DFACs define a matrix, and the matrix defines a network. The network is a network where the vertices are lines, not buses, and where the edges are the DFACs. And this is what the matrix representing which models this network looks like. The number of rows and the number of columns are equal to the number of lines and transformers in the system. And each element in the matrix is the DFACs associated with the outage of a particular line, which is a column, and the responding lines, which is each row. And the properties of the DFACs matrix are interesting. They're different from the properties of the Y-bus matrix. DFACs matrix is full. It's an M by M matrix. M is the number of lines. There are more lines than there are buses, so the DFACs matrix is a bigger matrix than Y-bus. It's full. There aren't very many zero terms because although each line is only directly connected to a few lines, it's indirectly connected to most of the lines in the system. That is, the outage of any one line will affect the flows on most of the other lines in the system. This connection is a physical connection. It's not necessarily a direct connection, but it's a connection due to the network as a whole. The DFACs matrix is not symmetrical. It measures the contagion and stress. It answers the question of whether an outage in one line might lead to overloading in another line, and therefore that other line going out of service as well. Now, this contagion or stress isn't just a function of DFACs. It also depends on the operating state. Let me show you some statistics of DFACs matrices. First, we're going to normalize the DFACs so that they all have values between -1 and +1. And I'll show you the statistics for two systems. One of them is part of the Eastern Interconnection of the United States and Canada, arguably the largest power system in the world. We're looking at just a piece of it, made up of 1,700 transmission lines and transformers. We'll also look at the entire Peruvian system, which is about 1/10 of the size of the piece of the Eastern Interconnection we're going to study. Here are the statistics for the DFACs for the Eastern Interconnection. Let's see, there are 1,700 lines with the DFACs coupling each pair of lines. That gives us about 3 million DFACs. This distribution function shows that all 3 million DFACs have absolute values greater than or equal to 0. It shows that about 10,000 of the DFACs have absolute values greater than or equal to 0.3, and about, 8,000 of them have DFACs greater than or equal to 0.5. Here is a similar diagram for the Peruvian system. And isn't this remarkable? That those two systems have a distribution function for the DFACs that looks the same. And that's remarkable because it would be hard to find two power systems that are more different than the Eastern Interconnection of the United States and Canada and the Peruvian national system. And although they look the same, there is a significant difference between the two of them. And that significant difference alone is worth the price of admission to this lecture. And it's a manifestation of what Vannevar Bush was talking about when he said that big systems are inherently less reliable than small systems. To see the difference, we'll plot both of these distribution functions on the same axes. What this shows is that big is, in fact, different, because the Eastern Interconnection has 10 times as many lines as the Peruvian system, but it has 20 times as many large defects than the Peruvian system does. That is, for the Eastern Interconnection, the piece of it that we studied, there are 20 times as many ways that an outage shifts a lot of power in another line. Or there are possibly 20 times the contagion and stress that the Peruvian system has. So this leads us to our first conclusion. That is that balkanizing, subdividing a large system, could increase its robustness by decreasing its vulnerability to cascading failures. Smaller systems may be less vulnerable to internal cascading since the defects are fewer. There are less defects, and especially if their values are lower, as for Peru compared to the Eastern Interconnection. This observation is new. I've never seen this said anywhere else. The next two observations are obvious and are already known. First one is, if you balkanize a system, if you subdivide a system into independent systems, you limit how big a cascading failure can be because the inter-system defects are zero. So a cascading failure in one subsystem can't propagate to another. Also, balkanizing reduces risk, that is, the exposure to failures in control and protective devices and practices and procedures to single subsystems. A problem in one system cannot affect another one. Now we're going to go back to the issue that I mentioned earlier, which is that the vulnerability to cascading isn't just a function of the defects, it's also a function of how the system is loaded. And we're going to study the loading of using the Eastern Interconnection. And we're going to measure loading using a statistic which we're calling rank, which measures the stress on the system. We're going to say that for each line and transformer, we're going to count 1 if the line is loaded over 75% of its rating. And we're going to count another, and we're going to add an additional 1 for each adjacent line that's loaded over 75% in the same direction, and an additional 1 for each other line with a defects greater than 0.3, with a fairly high defects that's loaded to more than 75% of its rating. We're going to look at what happens to these statistics when we increase the loading on the system. We're going to divide our piece of the Eastern Interconnection into 2 pieces. We're going to keep them connected to each other, but we're going to start by saying that the generation in each piece of the Eastern Interconnection is going to be enough to satisfy the demand in that piece of the interconnection, so that each of the 2 pieces of the interconnection are going to be self-sufficient. There will be no net flows between the 2. And for no net flows between the 2, this is the distribution function of the rank of the lines and transformers. Let's see, there are 1,700 of them. Therefore, there are 1,700 of them that have rank 0 or greater. I don't expect you to remember the definition of rank here, but large is worse. Large means that there's more stress. There are, 11 or 12 of them that have rank equal to 10. This is with 0 megawatts of net transfers from one region to the other. With 2,000 megawatts of net transfer, the statistics are the same. With 4,000 megawatts of net transfer, that is, increasing the generation in one side of the network and decreasing it in the other side, so that a net of 4,000 megawatts flows from one side of the system to the other side of the system. With 4,000 megawatts of net transfers, the statistics of stress, the rank statistics, change dramatically. And with 4,000 megawatts, they stay about the same. 6,000 megawatts, they stay about the same. And what does this say? What this says is that there's a tipping point, someplace between 2,000 and 4,000 megawatts, where all of a sudden, the statistics on rank, measuring the system as a whole, change dramatically. What can we conclude from this? Well, first, we already know that how a system is operated affects its vulnerability to blackouts. If there's a lot of power moving through the system, it's more vulnerable than if there isn't. But it's interesting that using the statistic for rank for stress that we used, as the loading increased beyond a point, the stress statistics changed dramatically too. In other words, the stress statistics changed in the same way what we already knew about the vulnerability to blackouts changed. That is, the stress statistics are related in some way to the vulnerability to the blackouts. That's kind of nice to know. And in particular, this occurred when the transfers between these two pieces of the system reached known limits. I know this system fairly well. I've done studies on it. And using conventional tools, I know roughly how much power can be transferred from one side of the system to the other. And the stress statistics reach their tipping point at about the point where those transfers reach the known transfer capability of the system. You might ask, why did so many statistics change at the same time? Why was it that all of the statistics seemed to get bigger? And this is because in a well-designed system like this one, there aren't any particular weak links. The system stresses simultaneously all over the system when it's too heavily loaded. Now we're going to turn to the country of Peru. In a much more complex study, we're going to look at two physical phenomena. The first one is the vulnerability of individual lines to cascading. That is, the vulnerability of a line to be overloaded if some other line fails, and therefore the overloaded line will also go out of service. And then we're looking at sort of the mirror image of that, which we're calling criticality, the typhoid Mary effect. That is, how many other lines will overload if a particular line goes out of service. So these are two different ways of looking at stress. We'll define statistics for each one of them. I'm not going to go into the details of the statistics, but like the statistic we used for the Eastern Interconnection study, big is worse. So large numbers mean greater vulnerability. Let me give you an example of such statistics. Before I do, let me tell you how we modeled our system. We looked at Peru 10 years out. We looked at optimistic, normal, and pessimistic load growth. For the different assumptions on load growth, we expanded the generation system in reasonable ways to match the load growth. We also expanded the transmission system with light expansion or medium expansion. And we looked at 12 months, peak, shoulder, and low hours, month by month. We were interested in daily effects, and we were also interested in important seasonal effects due to the hydro system. Now here are the statistics on vulnerability rank for 1 month. On the vertical axis, we have the number of lines. There are 169 lines, so 169 of them have rank vulnerability greater than or equal to 0. This is more easily seen if we plot this on semi-log paper. On semi-log paper, the thing becomes a straight line, and here are 40 lines that reach 100% or more of their capacity if there's an outage on some of the line. I've got to be careful the way I say this. I didn't say it quite right. It doesn't mean that there's one single line that will cause 40 other lines to overload. It means there are 40 lines that can overload, are subject to overloading if some other line overloads. It could be a different line. It could be 40 different lines, one for each of the overloaded lines. And here we have, I don't know, maybe a dozen lines that reach 150% or more of their rating with the outage of some other line. We use these models to study a very interesting relationship between congestion and stress. Let me tell you what congestion is. In power systems, the generation is dispatched in real time so as to satisfy the demand for power at the lowest possible fuel cost. This is an optimization problem that was formulated and solved in the 1930s. If this dispatch of generation would cause the transmission system to be overloaded someplace, then the system is considered to be congested. I have to comment that every real system I've ever seen is congested sometime, that there are always conditions under which a system can be congested. If the system is congested, then a redispatch is done. The power plants are redispatched to avoid overloading the system. This redispatch will always increase fuel costs, and therefore it's undesirable economically. The Peru study included high, medium, low, and very low congestion cases. Let me summarize a lot of work in one table that's kind of complicated. A table that relates congestion to stress or contagion. This is a very busy table. Let's look at two congestion scenarios. The one on the left in this orange oval is high congestion, the one on the right is medium congestion. In both cases, the load growth is optimistic. On the left, we have a light transmission expansion, and on the right, we have a medium transmission expansion. That is, on the right, there's more aluminum in the air. Now, the next 6 lines are statistics on vulnerability and criticality. And they are highly counterintuitive. You would think that the system that had the stronger transmission system would be less vulnerable to cascading. And yet what these statistics show is that's not the case. That the more congested system is less vulnerable to cascading. The more congested system is more vulnerable to cascading. The less congested system with a stronger transmission network has more cascading, or is more vulnerable to cascading. Why in the world? Why in the world should this be? This can't be right. Well, I'll give you 2 explanations. One of them is sort of a general one, and the other one is I'll talk about a very specific case which you already know about. The general explanation first. In the highly congested system, because of the congestion, there's a lot of redispatching of the generation to prevent overloading lines. In the less congested system, there isn't so much redispatch. Compared to the more congested system, more power can move greater distances in the less congested system. More power moving greater distances means more stress. Let me illustrate this with a specific example that we've already looked at. Think back to the 1965 blackout. 5 lines, remember, going from the Niagara Falls area to the Toronto area. If only one of those lines had been built, and if that one line had a relay that was set too low, that took that line out of service when it wasn't really overloaded, there wouldn't have been a blackout, because both the Canadian system and the New York system would have been able to handle the loss of that one blackout, or that one line. The cascading blackout occurred as a result of the failure of multiple lines connecting those two systems, which caused a loss in load that was significant, seen from the New York side, and a loss of generation that was significant, as seen from the Canadian side, and neither system could withstand that. Let's look at two other congestion scenarios. On the left, in the red oval, is a medium congestion scenario. On the right is a low congestion scenario. In both cases, demand growth is normal. Transmission expansion is light on the left and medium on the right. And again, the statistics show that the system is much more vulnerable to cascading with low congestion than it is with medium congestion. And then finally, in this violet oval, on the left is low congestion, on the right is very low congestion, pessimistic load growth, low load growth, the light transmission system on the left and the medium transmission system on the right, and the statistics are about the same for the two. Why are they the same? Because the demand for generation is, the demand for power is so low that the system isn't particularly congested by the economic dispatch. And the more powerful transmission system doesn't change the dispatch very much. Well, what can we conclude? With regard to planning, we can conclude that stress and congestion are different. In particular, the things that you do to fix congestion may make the stress worse. So what should we do? If we're interested in designing or planning the system to reduce the stress, to reduce the vulnerability and criticality, cascading blackouts, we ought to design the system to do that. If we want to, we ought to focus on that. And the way we do that is we identify and fix the most vulnerable and critical lines. This may require non-traditional fixes. We may do things that we wouldn't typically think of doing. I was involved in a case recently where the solution to prevent cascading was to take a line out of service. That would prevent the cascading. Something that I didn't point out when we looked at that table, but which you can see if you go back and look at it again, is that load growth increases stress. And this is true even if the transmission system is expanded. Why does it increase stress? Because more power is moving through the system. What can we conclude with regard to system operations? First, we can conclude that the system dispatchers ought to be monitoring the stress, the vulnerability and the criticality statistics in real time. If those statistics get to be high, they ought to take action. And what kind of action should they take? Well, right now, there is a function called security constrained dispatch. And the way it's used right now is that in an N-1 situation, that is, if a single contingency would cause a line to overload, then the system is redispatched so that on a single contingency, that line wouldn't overload. Well, that needs to be changed. We shouldn't just respond to N-1 overloaded lines, but we should respond to lines that are highly vulnerable or critical, even if they're not N-1 overloaded. Let's summarize what we've talked about. In fact, you summarize it for me, please. What are the causes of blackouts? Cascading blackouts are phenomena of what? Good. The phenomena of large systems, big is different. They're man-machine energy conversion systems. Cascading blackouts are triggered by what? Good. They're triggered by failures in control or protection devices, practices or procedures at a time when a system's under stress. Now this is important because there's no way that we can design or control or protective devices and implement practices or procedures that's fail-proof. These systems cannot operate perfectly 100% of the time. We do our best, but we still get blackouts. What we can do is we can reduce the stress on the system, because the blackouts do not occur when the system is not stressed. So analyzing vulnerability cascading. Traditional planning analyses aren't enough. Network theory provides new tools. Why aren't traditional planning analyses enough? They're not enough because they focus on the flow of power, which isn't really quite the issue in cascading blackouts. In fact, focusing on the flow of power, the models, the analysis that we do using traditional methods don't prevent blackouts from happening. They're still happening. Network theory provides some new and different tools which model how failures propagate, not how power moves, but how failures move. And they recognize that a statistical, not a probability analysis, of stress measures the network as a whole's vulnerability to cascading. Now, how is this different? How is what I'm proposing to you different from what we've already been doing? Let's look at it in a planning context. In planning, I'm going to simplify things a bit, but there's a bright line in system planning. By NERC criteria, which have the force of law in the United States, system has to be planned to N-1 conditions. That is, that if the worst contingency will cause a line to overload, then the system has to be fixed. And the bright line says that if under the worst contingency, the system is loaded to 101% of its capacity, of its rating, then you have to fix it. But if it's loaded to 99%, you don't. And the bright line says that if post-contingency, you have 20 lines that are operating at 95% of their capacity, that's okay, because they're not overloaded. And in fact, it's just as okay as if all lines were operating at less than 50% of their capacity. The network theory and stress model says, frankly, the bright line is a delusion. And you and I know this. You and I know that there's no difference between 101% loading and 99% loading. That difference is artificial. And stress is a condition of the network as a whole. You don't eliminate the stress just by looking at one line. This is in the planning context. How about in the system operating context? Well, in system operating, the traditional methods and the network theory and stress methods are also different. The stories word a little bit differently, but the differences are the same. Before I say goodbye, a few parting shots, things we don't know. There's a lot that we don't know, but here's some of them. One of them, is there a tipping point in size for criticality, vulnerability, and defect statistics? Stated another way, what's the maximum size for a robust system? That is, for a system that's inherently immune to cascading blackouts. If you're going to balkanize a system, how do you find the best cuts? Which statistics are the most helpful? Which statistics best measure the stress on the system? Vulnerability or criticality, rank or order, something else we haven't thought of yet, or do we have to use all of them? And finally, what options are available to us to reduce vulnerability and criticality? I have one other duty before I sign off, and that is that I need to express appreciation to my colleagues in Peru at the interconnected system operator who has responsibility for control and planning of the power system in Peru. The Peruvian results came from studies that I did with them. These studies have never been published. I'm grateful for their courtesy in allowing me to share these results with you. I also need to thank Jim Feltes of Siemens Power Technologies, who helped me with the analysis of the Eastern Interconnection study. Jim and my colleagues in Peru may not agree with all of my conclusions, but this work couldn't have been done without them, and I appreciate them. Thank you.